Welcome back. This is segment 2 of section 1.3. If you recall, we had already discussed the definition of all 6 of the basic trig functions using a coordinate definition, and we had illustrated a couple classes of fundamental identities. Those won't play a huge role for a while, but rather what I'd like to do is I'd like to work through a couple of problems that you might see in this chapter, and they're not terribly difficult. I want to do maybe one where we have to find certain values. I think I might have time to really do 2 basic ones, and then I'm going to assign some of these as homework problems, because I want you. There's actually some examples in the book that are pretty clear too. So let me, without further ado here, let me click over here to the document camera, and because these problems can take a little bit of time. Sorry, it's taking me just a second here. Okay, so I believe we were on page 3. Okay, so let's start with this example. Suppose, now remember, we had set these up so that there was an angle in standard position, and then this point P lies somewhere along the terminal ray. And so let's suppose that we've been given some information about this. So let's say, suppose point P is the coordinate 12, -5. Okay, so maybe it might help to draw this. So let's see what's going on here. So we've got an angle in standard position. So Q is here somewhere. Doesn't really matter where Q is. And let's see. So X is a positive number. Y is a negative number. So it doesn't have to be realistic. But P is maybe like right here, and it has the coordinate 12, -5. Okay, so maybe the directions on this are to find the exact value of each of the 6 trigonometric functions. For the associated angle theta. Okay, so just pause here for 1 second, because we don't really say how you're supposed to measure theta, except that we know how to measure theta from the previous sections. It's either a clockwise or a counterclockwise rotation from the initial ray to the terminal ray. And so it turns out we could measure this way, in which case theta would be like a negative angle, somewhere between -0 and -90 degrees. Or we could measure it from the initial ray counterclockwise all the way around, in which case this would be an angle, positive angle, somewhere between 270 degrees and 360. Or we could go around a complete revolution and then come back, in which case this would be somewhere between 430 and 450 and 540. But it doesn't make any difference, because the trig functions, the values of the angle are irrelevant. It doesn't matter how many times we've gone around or whether we're measuring in a positive or negative fashion, because it's really just defined by where this coordinate happens to be. So that's kind of, remember I had said earlier, I said, well, we're going to talk about these coterminal angles, and then it's going to turn out not to matter, because we're not so concerned, at least not in these early sections, we're not so concerned about the actual angle itself, or how, we're not talking about something revolving around. Like when we get to chapter 3, we start talking about circles and wheels and stuff, and then it does really matter how many times we've gone around or which direction we've gone. But for the purposes of the trig functions that are associated with angles, it does not matter how you've measured them. The value of a coterminal angle happens to be the sine of, say, an angle or a coterminal angle to that angle turns out to have exactly the same value because it's only based on these coordinates. And that's kind of a neat sort of property. So the first thing to do when we've got a setup like this is note that we'll just kind of make a little running list here. So we know that x is equal to 12, and we know that y is equal to -5. So now we need to find r, and r is going to be equal to the square root of x squared plus y squared, which, substituting the values, that's equal to the square root of, well, 12 squared plus -5 squared. Now remember, when you square a negative number, it's positive, right? For some reason, I don't know, sometimes people have been out of math classes for a while and they think that that's supposed to be negative. -5 times -5 is positive 25. So this, I'm not going to totally bore you with the arithmetic, but this is the square root of 169, which happens to be the number 13. Very convenient. So when we're trying to then write the values of sine and cosine, remember, we now have x, we have the values for x, y, and r, and we just need to use the definition. So remember, sine of theta, and I'm going to, not to be redundant, but I'm going to write it because this is only the second time you've seen it. So remember, sine of theta is equal to y over r, which happens to be, well, y is -5 and r is 13. So this is -5 over 13. And what I usually do is then I just write the reciprocal function because I know it's just going to be the reciprocal of that. So the cosecant of theta will be, flip this upside down, we have 13 over -5. Cosine, remember, is not y over r, but actually x over r, which happens to be, here x is 12, so this is 12 over 13. So secant of theta will be 13 over 12. And tangent, which is y over x or sine over cosine, however you want to do it, is -5 over 12. So cotangent, which is the reciprocal of tangent, is -12 over 5. I mean, we can put these negative signs out in front or whatever. I mean, that's some pretty basic algebra stuff. So let me just focus on this word because sometimes students don't really read this in the syllabus. Exact. Anytime you see a question that says you want the exact value, that means under no circumstances pull out your calculator and put some kind of a decimal approximation. Okay. At this point in your mathematical career, you know how to deal with fractions. And leave them this way. Don't like, this is 1 and a 12th. Do not do that. That's just confusing because 1 and a 12th sometimes starts to look like 11/12. Just leave them as improper fractions. We may have things that involve radicals because there's this square root function that happens to be in here. And so you have to be able to rationalize denominators, all those sorts of rules of simplification. It's quite possible we would have ended up with a fraction in here that had common factors in it, like 2 over 4. And so I feel at this point in your academic career, it's a reasonable expectation that you can simplify any sort of arithmetic expression. And I will try to point that out as it comes up. But just as an example, let me do another one maybe real quick. I think I can probably do 2 here. So without drawing all the bits and pieces here, let's use the exact same setup and just sort of say, okay, so let's say P is equal to, or sorry, let's not even give P. Let's say X is equal to -2 and R is equal to 4. Okay, so in this case, we don't have X and Y. but we have x and r, which means we should be able to find y. Note that this same formula could be used to solve for y if you had x and r, and it would look like this. You'd have y equal to, well, there's a problem here, and that is that we don't know whether y is positive or negative. So maybe if instead of this I say, how about, and theta is in quadrant 2. So that tells me, and maybe this is a little bit advanced for where we're at now, but notice that an angle in quadrant 2, this point, if it's in quadrant 2, is going to have a negative x value, but a positive y value. So this tells us that y is greater than 0. Well, at least greater than or equal to. So the formula, using the distance formula in reverse, where r is actually the distance, but now you want to find the coordinates, y is equal to, and again, it's going to be the positive square root of r squared minus x squared, okay, which happens to be equal to the square root of 16 minus 4, which is the square root of 12, which reduces down to 2 square root of 3. Now, again, this is a situation where that's not simplified. This is. We haven't really gotten formally into simplification of radicals, and I spend a little bit more time with that in, well, I mean, it comes up. But, once you have this sort of setup, the basics are still the same. So sine of theta is equal to y over r, which is 2 root 3 over 4. And notice here I have a factor in both the numerator and the denominator. This better be square root of 3 over 2, right? And so cosecant of theta will be 2 over square root of 3. Now, this is also improper. And if you remember from college algebra and probably even intermediate algebra, even beginning algebra, probably intermediate, the way to fix a monomial radical in the denominator is to multiply by enough factors to make this a whole number. So I'm going to multiply this by square root of 3 over square root of 3, and we end up with 2 root 3 over 3. Cosine is going to be a lot easier. So cosine of theta is x over r. So this is negative, sorry, let me go ahead and do it. X over r, which is negative 2 over 4, which happens to equal negative 1/2. So secant will be equal to the reciprocal of this, which is just simply negative 2. And tangent is y over x. So 2 root 3 over 2, which is just simply equal to square root of 3. Similarly, cotangent of theta is equal to 1 over square root of 3. Same problem as up here. So we multiply that by square root of 3 over square root of 3, and we end up with square root of 3 over 3. Okay, so there's a quick, dirty, another example where we had, maybe we didn't necessarily know where the point was, but we knew some things about it. We needed this extra information about which quadrant it was in to be able to pull this off, because it's possible that y could be either positive or negative. Okay, so let's move on to a similar kind of problem, but it's sort of set up in a whole different way. So let me just talk a little bit about how you would geometrically or how you would algebraically describe a ray. Okay, so a ray that begins at the origin So its initial point is the origin, can be described by the following equation. Excuse me. Y is equal to mx, where x is where x is either greater than or equal to 0, and this is where the ray is in Q1 or Q4, or alternatively, y equals mx, where x is less than or equal to 0, and this would be where that ray is in Q2 or Q3. So what the book uses is it's kind of this. Now this is from the equation of a line, right? I mean, it's y equals mx plus b, but for any ray that goes through that starts at the origin, the y-intercept is going to be 0. So all you're really seeing out of this is the slope. And this is why I was alluding to, it doesn't really have anything to do with the point itself. It has more to do with where, it's not the point on the ray that's important, it is actually the slope of the ray. But it is critical to understand that this extra little piece is what makes it a ray. Without that, it's a line. And so you need to have this sort of extra bit to describe what's going on. So what the book does is it kind of writes things like this. It says, suppose the terminal ray is defined by, and let's just, so 3x minus 2y equals 0, and x less than or equal to 0. Okay, so it might help to draw this. I don't know, maybe not. There aren't a lot of examples of this, and this is not a real useful way to do this, but it does come up. So note, it's pretty hard to draw lines if you don't have this in kind of standard form, which means this form, y equals mx. So if we solve this first and say, okay, well, this is negative 2y equal to negative 3x. So y is equal to 3/2 x. This tells us that the slope is 3/2. And this tells us that it's in either quadrant 2 or 3. So if we draw it, the only quadrant that will work where we have a positive slope is actually a quadrant 3 ray. Okay, so now here's what this question would then say. It's like, okay, well, go ahead and find all the trig values of this angle. Well, the problem is that the way we defined it has a coordinate, and you're like, well, what's x and what's y, and or some combination of it. It turns out that it doesn't really matter. You just find a point on that ray and work the details out. So the way to do that is to, generally speaking, is to pick a value of x not equal to 0 and substitute it in this equation to then find y. And then once you have x and y together, you can find r. So in this case, you got to be careful because x has to be negative. I would suggest substituting in -2 for x. So let's just make this statement. Let x equal -2. Thus, y equals -3, right? So if you substituted in -2 for x, you'd get -3 coming out. Hence, r equals the square root of x squared plus y squared, square root, which is equal to the square root of 2 squared, -2 squared, plus -3 squared. And what's that? That's 10 plus 9, square root of 13, which there's no way to reduce that. So now we have x, y, and r, we can do all the functions. And since this is like second or third time we've done this, sine of theta will be, remember it's y over r. So this is negative 3 over root 13, which I'm not going to bore you with the details. That's negative 3 root 13 over 13. No way to reduce this fraction. Similarly, the cosecant of the angle. Now, you don't want to necessarily use this one. Use this one because you can flip it upside down and you don't have to rationalize anything. So this becomes negative root 13 over 3. Cosine is x over r. So this is negative 2 over square root of 13, which again, you'll rationalize it, becomes negative 2 root 13 over 13. Secant is the reciprocal of this. So we've got negative square root of 13 over 2. And then finally, we've got tangent of theta. Remember, that's y over x. So negative 3 over negative 2, which is just positive 3/2. No need to rationalize anything. We don't have any radicals in there. So cotangent of theta, the reciprocal of this, is equal to 2 over 3. Okay, so again, just sort of a quick statement here. There are other ways to do this, and I think the book makes it far more complicated, where it says throw the equation in there and blah 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 blah, and it's like, I mean, really just pick a point, right? We picked x equal negative 2, but you could just as easily have picked x equal negative 1 or whatever, and you would end up with the same ratios, right? It would be more. This is probably the easiest one because it gets rid of this fraction. But you could certainly use, negative 4 or whatever else. You just got to make sure it's in the right domain for x, because that's kind of how the book writes these out. It says, well, here's the equation of a line, and we're going to restrict the domain so that it's only, either positive, non-negative, or non-positive. Okay, so I think for now, that's all I've got on these problems. There are several of them to try. But it may take some time to get familiar. I would say that the big thing to remember is you've got to memorize. Unfortunately, there is a lot of memorization in this class, but you have to memorize the definitions. And to remind you what I'm talking about, is I'm talking about these. When we go all the way back to the sort of the beginning of segment 1.1, segment 1, it's these definitions, okay? Because without these, we will get more complicated stuff where we maybe have some shortcuts or different things like that. But at the beginning, it's really critical that you memorize those. And also, as we work up to it, memorize both of those reciprocal, and memorize the reciprocal identities and the quotient identities, because they do make things a little bit easier to deal with. Okay, so I've got, there's one more topic that's in this section, which probably will not take a whole lot of time, but rather than drag this segment out, I will just start another video. But basically, we're going to look at, we have yet to say anything about these angles, right? Like, I don't know what that angle is. It could be, yeah, I just have no idea. Somewhere between, I know that it's somewhere between 180 degrees and 270, but I don't really know anything beyond that. What we will do in the remaining sections, well, once we get to chapter 2, is we're going to start trying to find some exact values for specific angles. But we can do, until we have a little bit more geometry skill, we can't really do that. But right now, we can do that for quadrant angles. And so it's kind of a little bit of a trick. I'll come back to it in the third and final segment. But for now, this is what we got. Okay, see you.